1, compared to the gear tooth on the rear sprocket on the left of small radius of a bicycle, a gear tooth on the front sprocket on the right of large radius has a faster linear speed and a faster angular speed, B, the same linear speed and a faster angular speed, C, a slower linear speed and a same angular speed, D, the same linear speed and a slower angular speed, or E, none of the above. Let's take a look.
All right, so we have these two places where this chain is connected to these wheels. And at both of those points, the linear speed is the same. Why is that? So all the points along this chain have the same linear speed, because if one point was moving faster than the other, one would catch up, and so you'd get like some sag in the chain. Or if one was moving faster than the other way, they'd break apart. And so the chain isn't grouping up or breaking apart. And so as a result, all of these points have the same linear speed. So what we see then is the one with the larger radius is going to have a smaller omega value. And we can use this kind of idea, and we can set the omega times r of this equal to the omega times r of that. And then we look at the ratio of the radiuses, tells me about the inverse of the ratio of the angular velocities.
Correct answer, D. Moving on, number 2, 2 points are on a disk that rotates about an axis perpendicular to the plane of the disk at its center. Point B is 3 times as far from the axis as point A. If the linear speed of point B is v, then the linear speed of point A, the closer one in, is going to be 9 times that speed, 3 times that speed, the same speed, a third that speed, or a ninth that speed. Let's take a look.
All right, so we have point B way out on the outside edge, and we have point A a little closer in. And we want to see what is the speed of A relative to B. So if B has a speed v at a radius r, I'll note that the radius at point A is a third that of B. So it's going to experience a third the speed. Correct answer, D.
Correct answer, D. All right, next one. A disk starts from rest and has a constant angular acceleration. If it takes a time t to make its first revolution, then in a time 2t, also starting from rest, the disk will make 2 revolutions, 4 revolutions, or 8 revolutions. Let's take a look.
So number 3. So it tells us it's a constant angular acceleration. That means we can use our 4 equations. I chose to use equation number 2 here. It tells us it starts at rest, and I'm going to choose theta naught to be 0. And so my relationship between the amount it turns, the angular acceleration, and the time is this. And so it does say that if we double the time, what happens to the amount it turns? So if we double that time, 2 squared, that's 4 times the theta, so your answer is B.
Correct answer, 4 revolutions. Number 4, a disk starts from rest and rotates with a constant angular acceleration. If the angular velocity is omega at the end of the first 2 revolutions, then at the end of 8 revolutions, it will be 2 times that omega, 4 times that omega, or 8 times that omega. Let's take a look.
All right, so we have a constant angular acceleration, so we can use these base equations. Starts at rest, and if I go ahead and experience an increase of 4 times the theta, what does that do to this omega? Well, 4 is something squared, so that something is 2, so we experience twice the acceleration. Correct answer, A there.
Correct answer, yes, 2 omega, A. Number 5, a stone of mass m is attached to a strong string and whirled in a vertical circle of radius r. At the exact top of the path, the tension in the string is 3 times the stone's weight. At this point, the stone's speed is which one of these options here? Let's take a look.
Okay, so the stone is at the top of its path. So we're going to draw our free body diagram here. So I have gravity acting down, I got tension acting down. They did tell me that tension was 3 mg. All right, so now I need to go ahead and sum up the forces parallel to the radius, set it equal to MAC. So I have mg plus tension equals MAC. So I end up with mg plus 3mg equals mac. So this is the start. So this is how I've gotten this side in terms of m. We'll see our m's cancel for us there. And so now I have 4g is equal to ac, but we want to know speed. So I have 4g is equal to v squared over r. So I get 4 times gr square rooted gives me v. They chose to, I guess, pull that 4 outside the square root, so 2 times the square root of gr there. So your correct answer is A.
Correct answer, A. Number 6. When a mass goes in a horizontal circle with speed v at the end of a string of length L on a frictionless table, the tension in the string is T. If the speed of that mass is doubled, but all else remains the same, the tension would be 2 times that tension, 4 times that tension, or half that tension. Let's take a look.
All right, so you got it going around in a circle. We're going to go ahead and double the speed and see how the tension goes. So we need a relationship between tension and speed. So I'm going to go ahead, sum up the forces parallel to the radius, set equal to mac. So because we're trying to find speed, we're going to make our substitution of v squared over there, r there. So I have tension is equal to m times v squared over r. And so doubling the speed is a squared term, so 2 squared is 4 times the tension. Correct answer there, B.
Correct answer, 4 times that tension. Number 7, when a mass goes in a horizontal circle with speed v at the end of a string of length L on a frictionless table, the tension in the string is T. If both speed of the mass and the length of the string are doubled, the tension would be 2T, 4T, or half T. Let's take a look.
Similar to the last one, now we're going to double the speed and the length. So we're doubling this radius as well. So I'm going to have 2 squared on top, 2 on the bottom. So 4 divided by 2, that's going to experience 2 times the tension. Correct answer there, A.
Correct answer, 2T there. All right. Number 8, objects in orbiting satellites are apparently weightless because they are too far from Earth to feel its gravity. B, Earth's gravitational pull is balanced by an outward centrifugal force. C, the Earth's gravitational pull is balanced by the centripetal force. And D, both. They and the satellite are in free fall toward the Earth because gravity is the only force acting on them. Let's take a look.
All right, so whenever you have something in orbit, the only force acting on it out there is gravity. And so whenever you have the situation where the only force acting on it is gravity, we call that free fall. Now, if something is in free fall, so let's take an example where we look at an elevator and we have a person standing in an elevator, there's a normal force, there's mg acting on them, and the normal force tells me about the apparent weight. So I want to try and figure out what's the apparent weight, the normal force, in a free fall situation. So what does the normal force have to be if the only force acting on it is gravity? Well, the normal force is going to be 0. So whenever you're in free fall, you're apparently weightless. So whether you're in free fall in an orbit or you're in free fall in an elevator, meaning the elevator cables have broken, you're in free fall, you will have a 0 apparent weight. And so if you ever have a situation where you're in an elevator and all of a sudden you're floating, you're in free fall. So sorry for that. Correct answer there, D.
Correct answer is D. If you had chose C, centripetal force, gravity is the centripetal force in this case. Number 9, if a planet had twice Earth's radius but only half its mass, the acceleration due to gravity at its surface would be which of the following? Big G, 2 times the acceleration of gravity, half the acceleration of gravity, a fourth, or an eighth that of what it is. Let's take a look.
All right, so we're dealing with the acceleration of gravity. So we're going to go ahead and use this equation here. And the question says, well, what if we do half the mass and twice the radius? So if I have half the mass and I have twice the radius, okay, so radius squared, so 2 squared on the bottom, that's a 4 on the bottom. Another 2 on the bottom, 2 times 4 is 8. And so we end up with an eighth, the acceleration of gravity there. Correct answer, E.
Correct answer, E. Number 10, 4 forces shown all have the same magnitude. Which force produces the greatest torque about point O, marked by the blue dot? Let's take a look.
All right, torque is dependent on three things: the size of the force, the direction of the force, and the location of the force. So if we want to figure out which one of these forces produces the largest torque, we want to find the largest force. Okay, they're all the same size, so they're all equal in that regard. We want to find the one that's most perpendicular. Well, that would be 1 and 3 qualify as that. F2 is completely parallel with the axis of rotation, so it's producing no torque. F4 kind of at an angle, so it's producing some torque. And then lastly, we want the one that's furthest, so we've narrowed it down to 1 and 3, so I see that 1 is furthest away. That gives me the correct answer of F1 is producing the most torque, so A.
Yes, F1 producing the most torque. Correct answer, A. Number 11, which of the four forces shown here produces a torque about the axis O that is directed out of the plane of the drawing? Let's take a look.
All right, so we're going to try and figure out which one of these four torques is out of the board, out of the plane here. F2 does not produce any torque, so it's not that one. So the rest of them we're going to have to use our right-hand rule for. So you start at your axis rotation and you point toward the force. And then let's do F1 first. You put your F finger in the direction of the force. So I keep that pointer finger along that axis rotation and I rotate so that my F finger is in the direction of the force and my thumb I see is pointing into the plane. Point toward F3, rotate with this parallel to that axis until my F finger points in the direction of F3, thumb's pointing into the board. Pointing to F4, okay, the perpendicular component is pointing down. If you wanted to, you could maybe bend it like that, but I do see my thumb is pointing out of the plane. So that is F4, correct answer there, D.
Yes, F4, D is the correct answer there. Number 12, a plumber pushes straight down on the end of a long wrench as shown. What is the magnitude of the torque he applies about the pipe at the lower end? Let's take a look.
To find torque, you need to find the perpendicular component of the force times the radius, or the distance from the axis of rotation which it's acting at. And so I see that this angle and this angle will be the same. Think about inclined planes when we did those. And so the component that's perpendicular is 900 cosine of 19 times its distance away. 0.8 will give me the torque. They only asked for the magnitude, but this is rotating in the counterclockwise or positive torque direction. So the correct answer there is C.
Correct answer, 900 cosine of 19 times that distance, 0.8. C is the correct answer there. 13, if the force on an object balance, then the object must be doing what? And there may be more than one correct answer. Let's take a look.
Okay, so we are looking at forces. Forces tell me about a change in linear motion. So forces only tell me about acceleration. So the only one of those choices, if the forces is 0, that tells me the acceleration is 0, and that's it. It only tells me the acceleration is 0. Therefore, we know it's not linearly accelerating. We don't know if it's moving, we don't know if it's rotating, we don't know if it's angularly accelerating. All we know is that it's not linearly accelerating, because that's all forces tell me about.
Yep, forces only tell me about acceleration, so D is the correct answer. If the torques on an object balance, then the object must what? Cannot be rotating, cannot have an angular acceleration, cannot be moving, or cannot be linearly accelerating. Let's take a look.
Okay, similar to the last one, torques are telling me about a change in rotational motion, so they're telling me about my alpha. So a net torque of 0 is only telling me that alpha is 0. That's all it's telling me. It's not telling me anything about, is it rotating, is it moving, is it linearly accelerating? It's just telling me that the angular acceleration is 0. So the correct answer there, B.
Correct answer, cannot have any angular acceleration. Yes, torques only tell me about angular acceleration. Number 15, a uniform beam is suspended horizontally as shown below. It is attached to the wall by a small hinge. The force that the hinge exerts on the beam has components of?
All right, so we have this scenario, and I'm trying to figure out what kind of forces am I applying with this hand here as it's touching. So one thing I can think about is that if I instead just put this purely vertical, now I have to apply a force down. Okay, and so that's because gravity is trying to cause it to rotate this way about that point. So that means the force from the wall has to be down as well. So that is the y component of the force. The other way to think about it is, for the x direction, that if the string is pulling it toward the wall must be pushing it out, away from the wall. And so we get a x component away from the wall. Oops, sorry. Push away from the wall, that x component, fx. So the correct answer there would be...
Yes, downward and to the left. D is the correct answer there.